مساء الخير عليكم. احنا النهاردة هناخد موضوع يعني جديد ومش جديد اللي هو ال Variable Sequential Sampling Plan، وهو ميكس ما بين ال Variable Sampling Plan اللي كنا خدناها وال Sequential Sampling Plan. طبعا to remind you, Sequential Sampling Plan refer to the plan in which we take item by item from the lot, and after selecting each item we inspect it and then we take one of the decision either to accept the lot, reject the lot, or to continue sampling. We took a sequential sampling plan in case of the attribute. Today we are going to take it in terms of a variable, meaning that an equality characteristic of interest is of a continuous type. So here we are talking about having equality characteristic of interest, which is x, and we assume that it has a normal distribution with mean mu and standard deviation sigma. Here in this chapter, we will assume that we have an upper specification limit USL. Remember that when we worked on a variable sampling plan, we assumed that we have lower specification limit. Actually, working on any of them, whether it would be the lower specification limit or the upper specification limit, will yield the same results. However, there would be some slight modification or minor modification regarding the direction and the addition or subtraction symbols or signs. And recall that when we need to design a sequential sampling plan, this implies to find the XA will XR, which represent the acceptable limit and the rejectable limit that satisfy a certain alpha and beta producer risk and a consumer risk. And the basic idea here is that after each item that we inspect, we will test whether the quality is acceptable or the quality is rejectable, or we need to continue sampling in order to be able to take a decision. Take into consideration that now, since we are working with the normal distribution, we are working in terms of el mu. And here we said that in el mu bit represent the average of the quality characteristic of interest. And if we are going to talk about the acceptable quality, we refer to it as mu1. And if we are going to talk about the rejectable quality, it's going to be referred to as el mu2. And recall that in the mu1 it represents the average of the quality characteristic that corresponds the existence of P1 defective item in the lot. And here el P1 bit represent an acceptable percentage of the defective items, while el mu2 bit represent an average of the quality characteristic that corresponds the existence of P2% of defective items, where in el P2 bit represent the rejectable level of a defective item. So the first question, in order to be able to design a variable sequential sampling plan and to be able to find el XA and XR, first we have to derive el mu1 and el mu2. Recall that in el mu1 and mu2 we depend on, we derive it depending on el P1 and el P2. Here the only difference from what we have discussed in a variable sampling plan is that we have an upper specification this time. This means that in the area after the upper specification limit bit represent a percent of a defective item. So whenever the quality characteristic of interest value exceeded an upper specification limit, we define a unit to be defective. So now if I need to drive in mu1, then I have to work on el P1. Working on el P1 meaning that it is, or it bit represent el percent that in el X bit exceeds el value upper specification limit, given that إنه el quality characteristic distribution is parameterized by el mu1. This is equal to probability Z. We standardize el X, so it is Z greater than upper specification limit minus el mu1 over is sigma. However, we need to work with the cumulative probability. So we take a complement, I work with the complement 1 minus probability Z less than. So now I can write a probability Z less than as phi اللي هي cumulative function of the standard normal distribution of the upper specification limit minus mu1 over is sigma. Then what we shall do is that we take L1 minus this side, so it would be 1 minus L P1, leaving here on the right side the L phi of USL minus mu1 over sigma. In this situation, we can get the inverse of CDF, phi inverse of L1 minus P1, which would be equal to this value. In this case, this means that we are searching for this value from the Z table such that the area on its left is equal to 1 minus P1. 1 minus P1 is a probability that exceeds the value 0.5. This means that this value اللي هي phi inverse 1 minus P1 is equivalent to a positive value, and this positive value is called ZP1. Here, working this out, you will find out that in the mu1 is equal to upper specification limit minus ZP1 sigma. Similarly, we can follow exactly the same steps while deriving a formula for mu2. In this situation, we shall work on P2, and it will have the same definition as P1, such that in the probability, it represents the probability that an X bit exceeds the upper specification limit, given that X has a parameter of mu2. Then I shall standardize X, so I would be having probability Z the greater than the upper specification limit minus mu2 over sigma. Then I shall work on the complement 1 minus probability Z less than USL minus mu2 over sigma, and then I shall put L1 minus in here, and I shall write this one as L phi of USL minus mu2 over sigma. In this case, I get L phi inverse of 1 minus P2, which will similarly be ZP2, and then we shall reach in mu2 is equal to the upper specification limit minus ZP2 sigma. By that, we have derived L mu1 and L mu2. Now we need to see how can we find the acceptable limit XA and the rejectable limit LXR. Because actually these are the main things we use in order to design a variable sequential sampling plan. So it would be the same as we have seen in the attribute sequential sampling plan. Again, we will depend on SPRT, sequential probability ratio test. And here according to the SPRT, the test statistic will be calculated after each item inspected from the lot. So after reaching M items, the test statistic will be the following likelihood ratio. F of x1 till xm given mu2, the rejectable average of a process, and divided by f of x1 till xm given mu1, the acceptable process average. And in this time, this is one of the main differences between a variable sequential sampling plan and the attribute sequential sampling plan, is that f of x here is the PDF of the normal distribution. So in this situation, we shall take this form of f of xi, we shall substitute in the numerator and in the denominator. In the numerator in terms of mu2 and in the denominator in terms of mu1, and then we shall see how the likelihood will reach. So here's the substitution. Now I can say that I can cancel this with that, and then I can take the exponent of LE in the denominator to be with the numerator like this. And then, as we said that, and for simplicity, we usually prefer to take the logarithm of LM, so we shall work with the ln of LM. And in this situation, we say that we continue sampling if ln LM is greater than ln capital A or less than ln capital R, or equivalently, we called ln capital A as a small a and ln capital R as small r. So we can say that, and we need to find ln LM. So this means that an E will be cancelled. So now we can work on the exponent. As you can see, we have half and sigma square that can be taken as a common factor. And then we shall work on expanding these two brackets and cancel the things with each other, or take the symbols that have a common form with each other. So here we took L2 sigma square as a common factor. Then we work it above in the denominator by expanding the brackets. As you can see, I can cancel xi square here with this xi square. And then I can take the mu1 squared with the mu2 squared together. And then I can take mu1 that is multiplied by xi with that mu2 multiplied by xi. And I shall take xi as a common factor, leaving out the summation notation. So now I can say that this is the form of the len LM. So now I can say that I will continue sampling if this quantity is between a certain value called a small a and a small r. Okay. So here, this is what we have done. So now I can work this out because actually I need to keep the summation xi in the middle and I don't need anything beside it. Because summation xi now, it's no longer but represent a cumulative number of a defective item as in the attribute sampling plans. However, now it bit represent a cumulative sum of the measurements till I reach unit I. يعني if you take the weights, فthis would be meaning that إن أنا I sum up the weights of all the units up till I reach item number M. So this means that إن أنا I need a summation xi to be in the middle because actually this is the object I depend on in taking a decision either to reject or to accept a lot or to continue sampling. So I will start first by entering a summation here and here. So in this case, I can say that in a summation will be entered on an xi and this is a constant would be left out. And then I shall take a summation for this quantity, which is a constant. So I'm leaving m outside or multiplied by m as follows. Here it is. So now I can take this quantity, I can take it on the right side and on the left side by an addition. And then I would be having still mu2 minus mu1 over sigma square multiplied by sigma of xi. Actually, I need summation xi to be standing alone inside the inequality, and this means that and then I need to divide both sides by mu2 minus mu1 over sigma square. Before the division, you have to make sure whether or not this is a positive quantity or a negative quantity. Because if it is a negative quantity, it's going to switch the inequality direction. So in this case, the question would be mu2 is larger than mu1 or mu1 is larger than mu2. In fact, work on the issue that you are working on the upper specification limit. Working on an upper specification limit means that the more the quality characteristic value increases, the more we go towards defining a defective item. So this means that the quality gets poorer whenever you approach the upper specification limit. So mu2 بتrefer to the rejectable average process and mu1 بتrepresent an acceptable average of the process. يبقى in this case, since mu2 is the rejectable one, this means that it is poor quality. يبقى this means that mu2 is greater than mu1 because as the x increase, this means that mu will increase with it. So if the mu have a high value, then this means that we are tending to have more poor level in the plot. يبقى in this case, mu2 is greater than mu1. يبقى in this situation, we can say that this quantity is positive because mu2 is greater than mu1. And this is only because I'm working on an upper specification limit. It wouldn't be the same case if I'm working with the lower specification limit. Think about it. Even in this case, I can divide both sides by this and keeping the direction of the inequality as it is. So here we have summation xi, and here we divided by both sides by the quantity mu2 minus mu1 over sigma square. Now I know that إنه الXA takes the form A over K plus MS, and I know that إنه الXR takes the form R over K plus MS. So in this situation, I can define Lk to be this quantity, mu2 minus mu1 over sigma square, and I can take the whole of this quantity and call it Ls. Then I shall reduce it somehow. This would be done by, here I can cancel sigma square along with sigma square, and then L2 would be in the denominator, so this becomes mu square 2 minus mu1 square over 2 mu2 minus mu1. So I can still expand this to the perfect bracket, so it's mu2 minus mu1 multiplied by mu2 plus mu1 divided by 2 multiplied by mu2 minus mu1. Then I shall cancel this with that, so what is left out is mu2 plus mu1 over L2. So this is S. So now we defined Lk and Ls, so now we can say we have derived the acceptable limit and the rejectable limit, and this means that we have designed the variable sequential sampling plan. So our decision should be continuous sampling if a summation xi is between these two values, and again, a summation xi, it is the cumulative summation of measurements taken from the first unit up to unit number n. And if it happens that in a summation xi is less than or equal to xa, we accept and stop, and summation xi is greater than xr, then our decision should be reject and stop. Here we say that in if some basic definition still didn't change from the attribute sequential sampling plan. The first one was in the len LM is still defined as a summation of kxi minus ks, which we call as a whole LZM, which we say that it is equal to summation zi, and so we still keeping the definition of zi to be kxi minus lks. And we are still preserving the definition of a Wald's approximation for the small a and the small r, as in the small a is equal to len capital A, which is approximately len beta over 1 minus alpha, and the small r to be len capital R, which is approximately len 1 minus beta over L alpha. So let's take an example on the variable sequential sampling plan. Using the following parameters اللي هما P1 alpha, P2 beta, USL and sigma equal to 200. One, we need to design a sequential sampling plan for a continuous quality characteristic with an upper specification limit only. Then we need to apply the previous plan if you know that 5 inspected units gave the following measurements. These are the 5 measurements respectively for the 5 units. Of course, using the given parameters, I can calculate L small a, small r, Lk, and Ls. Also, I can derive in mu1 and mu2 or calculate mu1 and mu2, because actually after each unit, I will be needing to find out whether in the mu is equal to mu1, the acceptable level, or that in h1 in the mu is equal to mu2, which is defined by this value. So in this case, we have reached LXA and LXR. So this is XA and this is XR, and our decision, and this is the design of the plan, and we will continue sampling if summation XI is between this formula or this formula. Okay, the second question was to apply this plan on 5 inspected items and see what result we shall reach. So here, as you can see, here is xi. This is the measurement we take for the ice unit. And this is the summation xi. This is the cumulative measurements. And here is the acceptable limit and a rejectable limit. As you can see here, the first one, the measurement was 4,454. So in this case, if I need to calculate the summation xi, so it would be the same, لأن I'm still in the first item. Then for each item, I have to calculate its acceptable limit and its rejectable limit. So in this case, since this is the first item, so m is equal to 1, so I have to substitute with m equal to 1 in each of them. And then I should compare between summation xi and both, and I will find out that I'm still in between them, so my decision would be continue sampling to a second item. The second item, this is the measurement of the second item. So in order to get a summation xi, I have to add these two items on each other. So I reached 9,202. Then I have to recalculate the acceptable limit and the rejectable limit by substituting with m equal to 2 in xa and xr, and I get these two values. If you compared a 9,202 among these two, you will find out that we are still in between LXA and LXR, so our decision would be the continue sampling. So I shall continue sampling to a third unit, 4,518, its measurement. Then I shall calculate its summation xi, which would be the sum of these three items as a whole. This is the value of summation xi. Recalculate xa and xr by substituting m equal to 3, and I still find that it is in between. Then in the fourth item, still summation xi, the sum of the four items, and I'm still in between the xa and xr. Then the last one, the fifth one, the summation xi would be the sum of the five items, so we reach 20 to 445, and comparing now between xa and xr that were calculated by substituting m with 5, you will find out that in the summation xi is lower than xa. Since it is lower than xa, then this means that our decision should be stop and accept the lot. So in this case, after inspecting the fifth item, we will stop sampling and accept the lot. The last thing we have is calculating the measures of a performance in a variable sequential sampling plan. Still similar to the attribute sequential sampling plan, we will be using or depending on the Wald's approximation to calculate a probability of acceptance, LASN, ATI, and the average outgoing quality, LAOQ. And we still depend on the same lemma in order to develop the approximation of these measures. As you can remember that in the lemma but depend on defining the variable zi, and the zi but takes positive values and negative values, and it depends when the expectation of zi is equal to 0 and when the expectation of zi is not equal to 0, and connect this with the solution of the moment generating function equalized by 1. So in this situation, still I have just told you that we still preserve the definition of zi being xik minus ks. So I need to know when exactly the expectation of zi would be equal to 0 and when exactly it will not be equal to 0. Remember that this is one of the main conditions I have to check each time I change the distribution in the sequential sampling plan. So here entering the expectation, so it would be expectation of xi multiplied by k minus ks, so this would be mu because xi follow normal distribution with mean mu. And if I would take k as a common factor, so I would be having left mu minus ls. Even in this case, expectation of zi will be equal to 0 if mu is equal to s. But if mu is not equal to s, then expectation zi is not going to be equal to 0. And then we should find the moment generating function of the variable zi and equalize it by 1 and then solve for t to find the value of lt. Here I'm working on xi. Well, xi we follow a normal distribution, and this is actually its moment generating function. And as you can see, it's e to the power t multiplied by a mean of x plus lt square multiplied by variance of x over 2. But I'm not working on x, I'm working on zi. Zi be represent linear combination in x. But this means that in zi is also following the normal distribution. The only thing left is to find its parameters, mu and sigma, our variance. You can directly deduce that in the Zi follows a normal with the following parameter. This is the mean and this is the variance. So now we can deduce the moment generating function of Zi where it is equal to e to the power t multiplied by اللي هي المين. we said that this is the mean of the variable, so we removed الميو بتاعت الx وحطينا الميو بتاعت الزي. و here we have اللي هي t square over 2 multiplied by sigma square, فاحنا شلنا السيجما سكوير بتاعت الx وحطينا الفاريانس بتاع الزي. Then we should equalize the moment generating function of z with 1 and then we solve it for t. هنا بقى يعني وده عكس اللي حصل في البرنولي وعكس اللي حصل في البواسون، ان احنا لما كنا بنعمل equalization ده ما كناش بنقدر نوصل على طول للتي، وقلنا ان احنا كنا محتاجين statistical software عشان نقدر ان احنا نوجد الفاليو بتاعت التي. هنا في النورمال it can easily be solved, this equation can easily be solved to deduce التي as انها function في الميو 1 والميو 2 and الميو. Of course هنا الميو 1 this is the اللي هو ال average of the quality characteristic corresponding to the acceptable level of the percent of defective item P1, والميو 2 هو ال average of the process corresponding to P2. الميو بقى هو ال average of the process that correspond the percent of defective items في اللوت اللي هي ال P. So if you do have the values of these three mu's, then you can find the value of LT. So this is the value of T that you should use whenever you have the condition mu not equal to LS. Then we shall work as usual as we did in an attribute sequential sampling plan. So we can say that and we can approximate a probability of acceptance like Wood presented it in two formulas. This one if mu is not equal to s, which corresponds to an expectation of zi is not equal to s, or this formula if it happens that n mu is equal to ls. And of course the t that we have just defined can be calculated and then substituted in this formula if mu is not equal to ls. Of course the AOQ we shall use the approximated formula for the AOQ, so we shall use the P multiplied by the PA. Then the average sampling number, and according to a Wold approximation, if you can remember, it was expectation of Zm over expectation of Zi, or expectation of Z square M over expectation of Z square I if it happens that an expectation of Zi is equal to 0. So still the definition provided or the approximation provided by Wold still valid in the variable case. So still we approximated Zm by A in case of acceptance and R in case of rejection, and accordingly we approximate Z square M by A square in terms of acceptance and R square in terms of rejection. And as for the expectation of Zi, this is the Zi, we enter the expectation, so we get mu k minus sk, and then here we square Zi and then we enter the expectation, so we reach at the end k square sigma square. لكن افتكروا هنا انه in order to find this we have to assume ان احنا we are working on the condition ان the expectation Zi equal to 0, which means that انه mu equal to ls. فهنا احنا each mu was removed and we replaced it by ls عشان تقدر ان هي to be reduced to this quantity k square sigma square. We take these, divide by each other بقى to find ASN. So as you can see, here is the ASN. In the case of mu not equal to s, and in case of in the mu is equal to ls. The last thing we have is the average total inspection, and as you can see that an average total inspection is apart from ASN, so actually we take this part in case of the acceptance and then we add a capital N in case of rejection. And here is the ATI, so this is the part from ASN I took plus the capital N1 minus the PA, and this is the part I took to inspect اللي هو the expected sample size in case of acceptance that I would inspect plus the capital N1 minus the PA in case of a rejection. And that's it.